Our speaker today is Timo Prusti, and it is a Gaia project scientist. He's since 2007. And he's joined the European Space Agency in the year 1993 as community support astronomer for the Infrared Space Observatory mission. And in year 2000, he joined the Herschel project scientist team, where he was involved in the planning for the operational phase of the mission. And he was, since 2003, deputy project scientist for Herschel mission. And his scientific interests fall under the topic related to star formation. This spans studies of young stars, clustering close by region to research of disks around the star. And at the moment, his work is focusing to utilize the Gaia DR2 data in studies of young stars. And of special attention are young stellar population in the Gould Belt region, both to probe star formation processes, but also to understand the Gould Belt. Okay, so Timo, if you could share your presentation.
Yeah, thanks for the words. Well, I will try to see if this one works. And do you see it?
Yes, please.
Good. Okay, so good afternoon, everyone. It's sort of funny to speak to a screen without seeing how many faces there are watching the screen, but in a way, the matter it shouldn't matter. So I'm going to talk about the Gaia, and I will have an overview of all aspects of the mission. So I will describe a little bit the spacecraft and instruments, how the mission is operated, and then I will focus on the scientific results so far. So the first thing is, why do we have a Gaia-like mission? And the reason for that one is that we want to know better how our own Milky Way is structured, how does it evolve, how was it born? And the difficulty, of course, in the topic is that we are inside the system. So we are inside the Milky Way disk. And we even lack the basic information that does our Milky Way galaxy have 4 or 2 spiral arms. We don't even know this kind of very basic things of it, simply because we are inside of it. And the Gaia method to probe our Milky Way galaxy is to use the stars as probes. So we are measuring stars. So what are we needing? We need to have the distances and motions of stars, but we also need to understand what kind of stars they are. So temperatures, ages, masses, chemical compositions. And we need to do it for a large sample. And sometimes when people ask that, okay, why is Gaia observing more than 1 billion stars? Wouldn't less be enough? But if you say that, well, 1 billion star is still less than 1% of the stars in the Milky Way, then very quickly the opinion changes, but is it enough? So this is like a compromise. It is a big sample, but we have to also realize that it's just a small fraction of the Milky Way stars what we are using, and then trying to deduce the properties of a Milky Way based on that sample. Now we have to go to space, because for the astrometry to get high angular accuracy measurements, you need to go to space. So with astrometry, we get the positions, also the distance. So that's why I have the 3D. And we get the proper motion, so the 2D velocities on the plane of the sky. The photometry, more specifically, this is spectrophotometry, is used to get the stellar properties. And then we have spectroscopy, but with a very dedicated instrument, not the generic spectroscopic instrument, but something we call radial velocity spectrograph. So that already reveals that the main thing of the spectrograph is to get the radial velocities. And this we can do to something like 150 million brightest stars. And that's what Gaia is all about. So a little bit of the mission. So Gaia is a European only, ESA only mission. So it's not a collaborative mission with other participants. We are already more than 6 years in space. We have completed our so-called nominal 5-year mission, and we are now in the extended part of the mission. I will come at the very end to the total length of the Gaia mission. And we are at L2, So this is like 1.5 million kilometers from Earth, other side of the moon. Idea to be there is that everything what we consider bad, so it's the moon, the Earth, and the sun, are at the same side. So when we turn our sun shield towards those disturbing objects, we have the dark skies to be observed. And then from that position, we observe the positions and parallaxes, etc. Of course, the key thing is that when we get telemetry from the satellite, that's not something what the scientists can use. So very essential part of this processing is so-called Data Processing and Analysis Consortium. So this is 450 scientists all over Europe in various places. And they have been really nominated by ESA to do this task. And they have been in place since 2007, formally already. Preparatory work started already before that. Everything is coded in Java, so several million lines of code. And the data collected from the spacecraft is 76 terabytes. So maybe the terabytes, it doesn't sound that impressive, but the amount of what is impressive is that we have had 145 billion star observations, and we just continue all the time more. We have had 2 data releases, one in 16 and the major one in 18, and we are now middle of the preparations for the next data release. Little bit the principle of the astrometry model. So what we can assume in a simple model for single stars, that they are moving in space with constant velocity. And so that is the true motion of the star. On top of that, because we are in L2, which is going around the sun once a year, we see the apparent motion. So this is where we can get the parallax measurement. So in the nominal 5-year mission, we see a star moving to one direction according to the proper motion and making all the loops, which are due to the apparent motion of the Earth going around the sun. So we can describe this motion with the proper motion and parallax and a reference position at a certain moment of time. And then we have 70 measurements on this red line. So that's essentially what Gaia is doing. You have 70 measurements on average on the red line, and based on that one, you calculate the best solution for the parallax and proper motion and position. Just a schematic picture of what the spacecraft looks like. So the main thing is a torus, which is our optical lens. We have 2 telescopes. 2 telescopes are necessary if you want to do absolute astrometry. But then we have only one focal plane. So what we are doing, we reflect these both fields of view to a single focal plane. So we do also need to have a bookkeeping system to know which star is coming from which field of view. This optical bench has to be extremely stable. That's required for the astrometry because we are not talking about arc seconds, we are not talking about milliarc seconds, but we are talking about microarc seconds. And really the heart of the system is the focal plane with 106 CCD detectors. And just to get a little bit the human size of this system, so you see the torus and you see the human beings assembling one of the telescopes, giving just you a little bit the scale of how big Gaia is. It is not small. It is a big satellite. Now the 106 CCDs are in the focal plane, which is sort of a meter by half a meter, roughly. So it is a huge thing itself. Key thing here is that we are a scanning telescope. So when we are observing stars, we are moving all the time. So how do you get sharp images if you're moving all the time? That can be achieved that we have perfectly matched the spin of the spacecraft and the reading of the CCDs. So we are actually having all the time an image of the sky on the CCDs. And while we are moving the image on the CCDs exactly with the same speed we are spinning. So we are all the time reading, integrating and reading the CCDs exactly in phase with spin. That's why how we get the sharp pictures. Now the parts of this focal plane are first starting from left are the sky mappers. So these 2 rows One is for field of view 1, one is for field of view 2. That's a detection system. So Gaia does not know anything of the sky in advance. It detects objects as it goes. And here we have the bookkeeping also, that whatever we later see in combined field of view, based on this sky mapper, we know from which field of view the objects are coming. For the astrometry, the main thing are the many dedicated CCDs to get the astrometric measurement. Many CCDs simply to improve the signal to noise. And then we have two rows for low resolution spectrophotometry. We have dedicated CCDs for blue part of the spectrum and dedicated CCDs for the red part of the spectrum. And finally, we have the high resolution spectroscopy. So this is the radial velocity spectrometer to get the radial velocities. Again, a picture just to give an impression of how big this focal plane is. You see the many CCDs being assembled in the Astrium premises. The photometer. So I'm talking about now the blue and red photometer. It is done with prisms. So it's actually very simple high school physics. We are using prisms. Of course, the manufacturing of these prisms, because they are rather big prisms, had to be done extremely carefully and tested very carefully and coated very homogeneously, etc. So it was an industrial challenge to get this kind of prisms on board. And when you look at the focal plane, you see the prisms are just in front of the dedicated CCDs for that one. Now then to the radial velocity spectrometer, it is a little bit more complicated box, also just in front of the dedicated CCDs. And what we are doing with RVS, we had to choose wavelength range. So it is in the red part where the calcium triplet is. And we observe that spectral region with resolution above 10,000. This of course means that this is very good wavelength range for cool stars. This is less good for hot stars because there are not really good lines for radial velocity determination in that range. But you have to find a compromise with this kind of mission. You cannot sort of have a variable spectroscopy available. Everything has to be very fixed in a spacecraft. And just an impression of the spectrometer. So that's a very busy box of all kind of glass wedges, and one of them is the grating, which is the key element to get the spectral resolution. Now this, I'm not going to go through the service module elements. I mean, you can imagine there are many engineering things which have to be solved, which has to be top of the notch things. So from this picture, I can only say that there is a question to all of you. How many people do you see in the service module? And the correct answer is 3. There is one, and here's the third one. That's just to give again the impression of what size of equipment we have in Gaia. Now we are getting closer to the launch. So this is in Kourou already, a few weeks before launch, because we have a sun shield which had to be opened. So there was before launch, there was a test that it can open. And here you see again the size of the whole satellite with respect to the human beings. If you're wondering what these big booms around the satellite are, so these are gravity compensation, because in space, when Gaia is open, when it opened the sun shield, there was no gravity. On Earth, there is of course gravity. So in order to have a representative test, you had to have a gravity compensation in order that the test was like what will happen in space. All that opening went smooth, so there was, in the end, no problem. And just a few pictures of the mounting. So you see the golden thing is the frigate, is the last phase of the mission, and Gaia is just being mated here with the frigate. And then we have the Soyuz rocket was assembled in Kourou by a Russian team, and just before mating with the fairing where the Gaia and the frigate were together. And then we had the launch, and at some point there's a project scientist wandering the sky that Gaia is sort of going and wishing all well, and all went well. Already the same day, ground-based people observed Gaia, and then it is just a stripe on the sky among many, many stars. So it disappeared to space very, very quickly in order to reach the L2 position, which where it got in 1 month's time. I'm not going to talk about the first half a year of commissioning. I'm just saying, want to make a comment that when you're busy with the satellite for many, many years and then you get the first light, I mean, it is an extreme happiness that things are working and look really good, even though every commissioning has its own problems. So that was a very busy time for all of us. But in the end, it all worked and we started the routine observations. A little bit how Gaia is seeing the sky. So there are a few things what has to be taken into account. One thing is because of thermal reasons, we are always keeping exactly 45-degree angle to the sun. And that's always the sun shield side, so that the telescope is not getting any variable exposure from the sun. We are a scanning satellite, so that means that we are doing one spin period every 6 hours. But then, in addition to this 6-hour spinning, we let the spin axis to precess. This precession is done in 70 days. So we always maintain the 45 degrees to the sun, but then the spin axis precesses around the sun in that period, while spinning in the scanning direction. And then, of course, on top of that one, the L2 goes around the sun in 1 year, and Gaia has a small orbit around the L2 because it's not like precisely in L2 where Gaia is, but going an orbit around that one. So what will happen then in practice is that when we try to see that how Gaia is seeing the sky, so if you first look the sun and the spin axis, and you see that Gaia is making these 6-hour scans and just getting great circles, you see the spin axis precessing, so that's the black dot, precessing very slowly. Sun is moving along the ecliptic even slower. Now speeding up a little bit, you can see that the 45 degrees is always kept with respect to the sun. And when the sun is moving, so we are covering the sky more and more homogeneously. And then after 5 years, you will see that we will have more or less symmetric pattern. So the parameters have been chosen in such a way that we have as homogeneous coverage of the sky as possible, taking into account the 45-degree angle constraint, what we have to keep always to the sun. Of course, ideal would be totally homogeneous sky, but that is not possible. So this is the best what we can do. So it always means that in ecliptic plane, the coverage is less than in ecliptic poles. So we finished the commissioning in summer 14, and where we are, you can always follow how we are observing on our website. So we have already passed the billions. So the number of astrometric measurements we count in trillions. So it's 1.4 trillion. We have 290 billion low-resolution photometric measurements, and we have 28 billion high-resolution spectra. I don't think anyone else has anything close to this kind of numbers available, and this is what we have observed so far, and we are continuing with this one. The magnitude limits, what we are doing astrometry and photometry down to almost 21st magnitude, and spectra for the radial velocity spectrometer, we have to stop at 16th magnitude. Obviously, the reason to stop spectra earlier is that when you spread the light, you don't have the same signal to noise. So you need brighter stars in order to have proper measurements. Bright stars are a problem to us, and also high density regions because we ran out of computing resources on board. So we have some special mapping data, what we do for all bright stars, and selected set of very crowded regions. But those are not yet processed, but we collect the data, because if we don't collect it now, we will never get it. Just a sort of very quick impression of the ground control. So this is really the control center in Darmstadt in Germany, where they are monitoring Gaia, but also Integral and XMM are in the same room. So it's just an office room with lots of terminals where people are in contact with the spacecraft and give the commanding and react if there is something wrong with any of these satellites. Anything what we change on board in Gaia, we have a representative electric copy of Gaia test in the office. So everything is connected. So anything what we want to change, before we change it on board, we test it in Darmstadt in this Avionics module. And it is sort of, I think, funny thing like this one. Don't throw anything away. And it's a very busy, lots of electric cables and trying to have everything what we have in Gaia as well, so that we can truly test what would happen with the new software update, for example. I mentioned already the SkyMapper image, but let me show here. We are in principle not making images. We have an image all the time of the whole sky, but if we would like to send that one down, we would just, there is no telemetry possibility to get so much data down. So typically, all these maps, what Gaia is seeing in flight, we only make tiny little extracts of the point sources and have a tiny little window sent of the point sources in the map. All the rest, unfortunately, we have to throw away. There are these exceptions, what I mentioned earlier, the crowded regions and the very bright stars, where we do use these maps and send them down. So we can afford to do a little bit of that. So here is just an example of the galactic center region, and the moon is there just for the scale. So what Gaia can do is to map incredibly quickly huge patches of the sky in essentially with the Hubble Space Telescope spatial resolution. Now moving to the science, so I go to the latest data release, which is now almost 2 years ago, in April in 18. So the main thing is that what we got, which people are using a lot, are the parallaxes and proper motions. So 1.3 billion stars have parallaxes, proper motions, and also photometry in red and blue. By far, most of the papers have been using this data from the release. But we should not forget a very relevant release element, also 7 million radial velocities. It looks here like a small ball, sort of almost like irrelevant, but this is by far the biggest collection of radial velocities ever achieved, and of course everything in a homogeneous system. So that has been extensively used in studies of the Milky Way and galactic structure. Just not trying to explain all the curves. So the top one, which is the Gaia DR2, so the sort of violet colored one, it gives the sort of number counts of sources on the brightness. So anything, of course, which is very bright, it's below brighter than 5th magnitude. There we are not complete because the visible stars are simply too bright for Gaia. We can do everything between sort of 6 and 12 with tricks on board, otherwise we would saturate. The sort of prime domain of Gaia is really from the 13th, 14th magnitude to 21, where we are getting the full capability of the mission. And of course, because of the luminosity function, the hundreds of millions of stars, most of them are faint. The only thing what I want to here that you pay attention. So we have the overall release, which is this curve, but then I would like to focus on the on this curve, which is the Gaia optical reference frame objects. These are mostly quasars, and the important thing here is that because we do see also a lot of quasars, we can check our astrometry, because quasars you expect to be far away, parallax essentially 0, and we expect them also to not to move, so proper motion 0. We are not using that information when we do astrometry. We do absolute astrometry without that knowledge, and then we use these objects to check the quality of our measurement. And we can this way we can control the systematics in our processing. So we have, for example, we have an offset from the 0-point parallax. So rather than correcting it, we document it so that people can address the issue as they best wish. something of the parallax accuracy. So before Gaia, we had Hipparchus, and we had sort of 120,000 stars, bright stars, and with the parallax accuracy of few hundred microarcsecond. When Gaia, the first data release came, we could go about the same accuracy, a little bit fainter. So we went from Hipparchus 120,000 stars to 2 million stars. And now with Gaia DR2, that's really when we go to 1.3 billion stars. So we go both for more accurate. So the bright stars are roughly here. And then we have the faint stars, which are essentially photon noise limited observations. And we have indeed, instead of thousands or millions, we have more than 1 billion stars. This is with the photometric accuracy, and I like to show it in signal to noise ratio and have a couple of remarks on that one. So first, if you look at the very bright stars, so these are the visual stars, you see that the signal to noise ratio is not very impressive. I mean, still quite good, I would say, but not as good as it could be. The reason here is that whatever we try to do on board, all these stars saturate. So we are trying to do photometry on saturated sources, which I think everyone can understand is complicated. Then when we go to the bright stars, for Gaia bright stars, which is around from 6 to sort of 13th magnitude, we have incredible signal to noise ratio. You see here all kind of wiggles, and what these wiggles are that we have to have different kind of configurations on board in order to cope with this enormous dynamic range. So the wiggles are in a way indication that we are not doing the calibration perfectly, but if you look in what kind of signal to noise domain we are, in a way we are with answering that is well below 1 millimagnitude. So it's not really worrying in sort of using this data in that sense. And then we have just the signal to noise going down as we ran out of photons, but you can see that even at 20th magnitude, we have a signal to noise of about 100. So there is an incredible dynamic range in Gaia with the whole range with very high photometric accuracy. For the radial velocities, we are typically below half a kilometer per second. For radial velocity, we actually like bright stars because we want to have the photons, so that's not a problem. Then already with the second data release, you start to see that we run out of photons or signal to noise when we start to get fainter than 10th magnitude. This will improve with time because we have more data, so we will already go much deeper in the coming release. Second thing what you see here is that we are good in cool stars, and the hotter the star gets, the more difficult it gets with the radial velocity determination. Just one word from the accuracy. So this is the previous was about precision. So this is really trying to compare the accuracies with different surveys, because in the end you want to have the radial velocities to be in the same velocity system as the astrometry. And it's far from trivial to have an absolute radial velocity determination. It's more complicated than one would think at the first instance. But we are within a few hundred meters of a second in the right track in there. Now, just a little bit showing of what kind of results are getting. So we are mapping the skies. So this is first the constellations just to orient you, and then we are going to go to Taurus towards the Hyades and Pleiades. And you see that when you see the sky in a sort of this kind of 3D simulation, the 3D element of the data becomes visible. If you are just seeing the flat sky, of course, you cannot sort of appreciate that we have deduced the distances. So if it stops like now, then you don't see the distances. So you do need, we have the distances, so we have to do this kind of computer animations, of course, more for scientific purposes, in order to utilize the three-dimensional information what Gaia can provide us. But of course, it's not only the parallaxes which give the distances, we also have the proper motions, so how the stars are moving. And that's of course essential in when we want to understand how the dynamics in our Milky Way galaxy are playing a role. And this kind of image always is a sort of nice thing to see that everything is moving. I mean, nothing is really constant. I don't think we know that all stars have proper motions, but when you see it, you really start to appreciate that it is actually rather tricky. This was what the sky looked after the first Gaia data release. So if you remember the video I showed about the scanning law, you can very clearly see here elements of that scanning law. Now this one is in galactic coordinates, so the bad spots are a little bit different. So when we made 2 years ago the data release 2 with more data, many of the sort of observational features disappeared. And of course the big advantage what we had was that we have the color. So not only the star counts, but also color. And then you start to see all the familiar regions in our, what you can see in the galactic pictures. You can see the dark clouds because simply behind there are no stars. But you can also see extragalactic objects like the Magellanic Clouds. So although we are primarily seeing stars in our Milky Way, we can also probe our local group galaxies and globular clusters around our Milky Way. If you have an idea of the color and you have an idea of the positions, you can do extinction map. Now this one looks very familiar. We can recognize all the known clouds from our solar neighborhood in this one and the galactic plane. And this one is just simply the radial velocity. So averaging the radial velocities in certain bin on the sky. And what do you see here? Because everything in Gaia is determined with respect to the barycenter. So you see the solar motion around in our galaxy. Of course, when you start looking details, you see that is there in the center is the signature of the bar of the Milky Way. But in the first instance, what you see here is that Milky Way is rotating, which is not really a surprise. But when you see it like this, I think it is quite impressive. So now I will go move into a selected set of science results. I will try to cover all of them. The only thing, the last one, the celestial reference frame, I already mentioned it with the quasars, but the rest I try to give a quick result of something. This is a Hubble image of some dense region on the sky, and what you of course see that stars have colors. Now we do have exactly the same information. We have also colors. So when you start binning the information together, you have the color information from Gaia, but we also have the distance information. So if you scale everything to distance with the distance, you get the absolute magnitude color diagram, of course, the Hertzsprung-Russell diagram. And I don't need to tell to this audience that, of course, the HR diagram is one of the fundamentals of our understanding of stellar evolution. Just that the quality what we can get now with the Gaia data, because of the good parallaxes, we can see all the features very clearly. And when you start to look, we have really a big sample, so something like white dwarfs, we see very, very clearly the main sequence is very clear. Everything becomes very clear simply because of the huge number of objects that we can confidently put in this kind of diagram. So if I look the white dwarfs separately, so there are a couple of things what you see immediately. You see that it splits into two. So this is really to do with the specific features of white dwarfs. And then there is a third one, very faint feature, the leftmost arrow. You see a sort of spur coming out from the main feature of the white dwarfs. And this one has an explanation. It's due to white dwarf crystallization. So I like this result a lot because there is a prediction that white dwarfs have a crystallization in their cores. The prediction was made 50 years ago, but it could never be proven observationally. And now we see the feature in Gaia data. And what is happening when the white dwarfs are cooling down in the cooling sequence, they stop for 1 billion years in this crystallization feature because their crystallization takes stops the cooling. And then after the crystallization is completed, the cooling of the white dwarfs continues. And of course, if you're using white dwarfs as probes of the previous star formation history in Milky Way, you better know the theoretical evolution of white dwarfs, because otherwise you might get things 1 billion years off from your model. Another thing what is can be, again, going back to the HR diagram, is that you can look variable stars. And of course, because for astrometry we are having several epochs of each star, we can also look how, not only how the brightness is changing, but also how the color is changing with this brightness change. So for example, Cepheids, which are the green dots at the upper part of the diagram, so they are pulsating stars, so they are pulsating and getting changing both the color and brightness at the same time. And the interesting thing, of course, with the Cepheids is that there is so-called period luminosity relation. So first of all, they are bright, so we can see Cepheids also in other galaxies. And if we can just monitor in the light, we can get the periodicity. And then we have the luminosity. So then observing the observed magnitude, we can get the distance also to external galaxies. But of course, it's very important that you have anchored this period luminosity relation to something. And this is anchored to geometric distances. The importance of this one can be sort of found that immediately Adam Riess is, of course, a Nobel laureate. So he also went into the Gaia data and started to deduce what is the period luminosity relation based on Gaia data from the known Cepheids, which are in our Milky Way, so that you can calibrate this distance ladder. And after this careful study, what he did, he came to the conclusion that based on Gaia data, he comes to a Hubble constant. Of course, I mean, he used the other steps as well, but the Gaia is in the first step to 70, roughly 74. And this is, of course, one of the things which is the so-called tension, that if you look at the Planck result, which is well below 70, there is a mismatch which starts to be already at a very high confidence level, a true mismatch. And that is, of course, an open question in astrophysics, that why, if you look at the current measurements, why do we get a different Hubble constant that if you look for the very old, in a way, the beginning of the universe data? And where is this discrepancy coming from? I think more or less everyone is agreeing that it's not in the data reduction, but there is something in fundamental in physics what we don't understand. But that I leave to the specialists. Moving on with the Hubble diagram, one of the things, if one selects based on the velocity, because we have the velocities from Gaia, and then you can see that there are like some of the sequences split into two. And this is a metallicity effect. So there are clearly two populations in the high velocity stars. And not directly related to the metallicity division, but there was a study by Helmi and collaborators who looked at the motion of stars. And what you see here is that in a certain diagram, you see that the thin disk stars should all have positive velocities. But there is a big group of stars which have negative velocity. So this means these blue stars, they are rotating in the Milky Way to the opposite direction as most of the other stars. So this is, of course, very peculiar. And the explanation is that something like 10 billion years ago, we had a big merger in our Milky Way. So Milky Way was at that time much smaller galaxy, and it was a sort of 1-to-4 ratio merger. And in 10 billion years time, all these merger stars, they are everywhere. So if you think you are observing at some specific point in this blue galaxy, you see that the red stars, so those are the intruders, they are in all directions. So it's very difficult to find them. However, we have something very nice in physics, like conservation of angular momentum. So they came to the wrong direction, well, luckily in a way, because then we can easily see them, and they keep the wrong direction. So we can find these stars from this old merger because they still go around in our Milky Way in the wrong direction. If you look now stars a little bit closer, going to the next study, so it looks like a mess. The velocities are it's very difficult to make sort of sense of this kind of plots where velocities go to all directions. So it was already known, this is now in Cartesian coordinates, velocities of stars in our solar neighborhood, based on Hipparcos and ground-based spectroscopy. You start to see some sort of features that it's not like just everyone all moving in certain direction with a dispersion. When the first Gaia data release came, it's still not clear, but it looks like there is some structure. And when Gaia data release 2 came, and then it was using the velocities also from Gaia, you really see that there are features, there are kind of streaks and gaps. And then the question is, of course, so what is happening? What are these features in our solar neighborhood? It is kind of described that it's like ripples in our Milky Way. And it gets a little bit complicated. So first here is a sort of setup of which stars we see. We have this 6-dimensional information in Gaia. You see that they are all in the solar neighborhood, quite far away from the galactic center. So we're really talking about the solar neighborhood stars. And you have to play quite with the data before you get to the phase that you see something what we call a snail shell structure. So you have a mixing of the velocities up and down depending on the distance from the galactic plane. The same thing, if one is looking at the phi velocities as a function of the galactic distance, you see these streaks. And if one is doing modeling, so this is a model where you have a galactic disk and then you disturb it with something a few 100 million years ago. And what you get the snail shell structure, you get the streaks into the velocity structures. So what is the anticipation here is that we can, if we have the disk in a more or less stable system and then something hits it, something like 500 million years ago, you get this sort of mixing of the phase space. You get this snail form to the velocities. And if one tries to then find the reason what could have happened, it could be that Sagittarius dwarf galaxy, which had then was going close to the galactic disk, has caused this one. Just to show the place in the Gaia map of the Sagittarius dwarf, the reason why it has not been known that long time is that it's of course very close to the galactic center. So it's hidden into the high density region and high extinction region. So it was discovered only in '94. Now we know that there are lots of streams around. So it has been losing stars over the, when it's been going around our Milky Way galaxy. And the last perigalactic passage was about 500 million years ago. So maybe this is the reason why we see all these ripples and phase mixing in our solar neighborhood. But I have to say that since this discovery, everyone agrees that there is something disturbing the motions of stars around the sun. But there are also different proposals that it could be the bar buckling, or there are several candidates what could be causing it. Just keeping with the Sagittarius dwarf, there is also a discussion that this may be reason to causing the warp in our disk. So the warp is the bending modes far away from the sun in the outer parts of the Milky Way. So with this recent study by Poggio and collaborators, they showed that this warp is not static. They also could calculate the rotation time of this warp, and they got something like 600 to 700 million years compared to sun, which takes 220 million years to go around the galactic center. And deducing from the speed of the warp is that it's not consistent with many models, and they also go to the Sagittarius dwarf. So it seems to be like Sagittarius dwarf galaxy is a favorite of everyone causing disturbances. And you can see this. Film in ESA website. It is worth. It gives a good impression of how the sun is going quicker than the warp. But you have to sort of concentrate on it a little bit if you want to get the full idea of it. Okay, let me move to the next one. I go to the Gould Belt. I mean, this I think is a sort of funny story. Gould Belt is something discovered already around the mid 19th century. And more than 100 years ago, there has been already speculation that this belt is actually a ring and the sun is somehow not in the center of the ring, but somewhere inside of it. There were already hints that maybe it is not a ring, and I think now it's confirmed by a recent paper by Alves and collaborators that there is no ring. It is actually a sinusoidal wave where the stars are just, they could trace it to 2 kiloparsec and there is an amplitude of 160 parsec. So the interesting thing, of course, will be that when we get the next data release coming later this year, we can study this in more detail. But I think the bigger question is, again, a disturbance we can see somewhere close to our sun. What can be the reason causing this kind of disturbances? Very quickly, just going through the also a little bit further away from in our galaxy to globular clusters and local group galaxies. So given the Gaia data, we can get finally some information of the orbits of these objects along the Milky Way, and both for the globular clusters, but also for the local group galaxies. And the interesting thing, what is found with the local group galaxies, that if you take certain regions of the sky, you can see that there seem to be common motions, whatever then that will tell to us. One thing what we see very clearly is a large Magellanic Cloud, so almost 8 million stars in Magellanic Cloud. So again, enough stars to do statistical studies. And when people took out the proper motion of the Magellanic Cloud itself and just look the residuals, this is what you get. And you don't need to be an expert to say, it's the rotation. And I mean, people have been decades trying to find out, is large Magellanic Cloud rotating? And with Gaia, it's just a snap of fingers and you see, yes, you can detect the rotation of Magellanic Cloud. And the artistic version of the same thing. Solar system objects, just very briefly to say that this is the O-C. So this is the observed versus calculated offset in the scanning direction in milliarc seconds. Of course, the asteroid people were used to get the accuracies which are not fitting into this image because typically they were several tens of milliarc seconds. Now with Gaia, we go to the few milliarc second for the bright asteroids, and only at the faint ones we go to sort of 10 milliarc second accuracy. But this is something what the community has never seen before. And they are really looking at into the orbits of solar system objects, and especially the big thing will be that we have also spectrophotometry of the asteroids. So when you have very accurate orbits, you can ask the question, do we see also properties of the asteroids which have something to do with the orbit class of them? So you are trying to sort of find the hints of the origin of our solar system with this data. And there is a lot of information in the orbits of these objects. Now, this is one of my favorites of solar system topic. What you see here is the bright object is Neptune. And what you see just above the Neptune is a bright star. If the bright star would not be there, you would see Triton, a moon of Neptune. But because it's so close, you see only the bright star. And what is happening here, this is just before the Triton moon is going in front of the bright star. And what is the Gaia role here is that because we are actually going to observe the shadow of the star by Triton on Earth, and that shadow on Earth is very small, few tens of kilometers. So you need very accurate positions both for the Triton and the star, because otherwise you don't know where the shadow is on Earth. And thanks to Gaia, we could guide the people to go exactly to the right place to make observation. And when I put this running, I think you should focus, don't look at the Neptune, just look at the bright, don't look at the graph what is appearing, you can look it afterwards, just look at the star which is just above Neptune in this observing track. So this is just before. Now we are in the shadow. Just continue looking for the bright star above Neptune. Hope you got that one. Something happened right in the middle of the moment that the shadow was crossing the Earth, and now the event is over, and we are back to the normal situation. So what happened here? We saw the occultation of the star, and right in the middle of it, because we could fine-tune the position of the observer so fine that it's perfectly aligned with the star moon Earth line. It's the moment when the light is bending to the atmosphere of the moon, and by observing this central flash due to bending of light, you can actually address the issue of pressure on the moon surface. So I think it's quite fascinating that just by doing good astrometry, you can actually make crucial steps to help understanding the atmospheres of moons better. Then I move into different kind of light bending, gravitational light bending. We have also something called Gaia alert. So every day we also look what Gaia is seeing, and if there is something like what happened here, these are the Gaia measurements. There was a brightening of 1 magnitude, an alert is made, and after that many ground-based observatories in different colors were following, and you see that the light curve behavior is very peculiar. So what is happening here is that in the coming 500 days, one could see this complicated structure, and you can explain it with gravitational bending, where you have a binary star, which is quite a rapid short period binary, so that the configuration where you get this, this gravitational lensing is changing during the period that this event is taking place. So these were two low mass stars in a binary system, which caused this one. And I think the really exciting thing for the future is that exactly at the moment we had one of these excess things that it really got bright. So it's one of these peculiar configurations. We made Gaia measurements. So when we get the astrometry reduced, we can get the astrometric effect of microlensing. I think because I'm short of time, so I will go a little bit speed up. Just want to mention of the archive use that are people using our archive? Yes, they are. So typically nowadays we have every month 5,000 unique users of the archive. So I think the data what we are providing is really widely used and also published. So last year we had an absolute record of more than 1,000 papers. So that means these are refereed papers. This means that in a typical day there are sort of 3 to 4 Gaia papers appearing in the literature. So you can imagine also that when I make you a highlight presentation, I have to be quite rough what to choose, because there is no way to give an overview of 1,400 papers. And just if looking, so there is a different statistics, only looking for the Gaia DR2 papers, refereed or non-refereed, so there is a compilation of that. And I looked at what are the keywords, so you can see the sort of stars, kinematics, galactic structure, open clusters. Planets and satellites may look funny, but this is also where exoplanets are, because the Gaia data is extremely important for exoplanets. Not yet for the exoplanets themselves, that will be later, but now, because you need to know the properties of the host star. If you know the properties of the host star, you can much better constrain the properties of the exoplanet around the object. And white dwarfs, you see, is a big topic, etc. So it's very anticipated which topics are mostly addressed in Gaia. Finally, just moving to the end of it, wanted to say what is the future. So Gaia will not live forever. We have a prediction of the end of mission December 24 with a few months uncertainty. So that will be the true end of mission, but okay, then we have had like 10 years of measurements, and I think it's quite fantastic if we can truly achieve that one, that nothing else goes wrong with the spacecraft before that. We are heading towards the data release. We are actually very busy now rounding it off and hope to get it after summer. This will be an update of the photometry and astrometry. And then a very big release 2021, the complete data release 3, which will be the same photometry and astrometry as in this EDR. So the EDR is early data release 3, but then also all the astrophysical parameters, radial velocities, variable stars, solar system objects, orbit calculations, they will all be in the data release 3 proper. And I hope that I have made the audience enthusiastic enough to think about using these data themselves in their research. And I just leave an image to conclude my presentation. And I suppose we can take some questions as well.
Yes, thank you very much for the very nice presentation. The 3 papers per day, so very nice. I mean, do you have time to read it, all of them? Could you hear me?
Yeah, sorry, what did you say?
I say just that it's very nice to have 3 papers per day.
Yes.
From the Gaia results, if you have time to read it.
No, it doesn't work, unfortunately. I try to read all the titles and selected abstracts, and then I have to also trust. I go to conferences and learn what people are presenting of Gaia data in order to make the selection of good papers. No, it's impossible to read all of them. It's just too much. It's a luxury problem.
Yeah, nice. Well, we have so far 17 questions. Let me a little bit encourage audience to vote at Slido, and I will go through them. Okay. So the first one: which project or experiment from space exploration history do you like most?
Well, I'm partial in this one. I think Gaia is the most fantastic thing, and I think in a way it's not only that I'm working on it, but I think the publication numbers and the usage numbers of the archive also tell that we are really with the gold mine here.
So Gaia, okay, so I will switch to another question, which is a little bit in connection with this one, that it's, if you could have a budget like James Webb Space Telescope, so approximately $10 billion, what space mission experiment you will like to see to become reality?
So what we are now actually already planning, but it's exactly that it's a little bit too expensive. But with 10 billion, I think we could get a long way ahead. We are already looking into the follow-up of Gaia, but in the near-infrared wavelengths. So basically doing the same thing what Gaia has done, but in the near-infrared, so that we could see better through to star-forming regions and through the disk. But at the same time having a large enough number of common stars so that you have a long time baseline between Gaia and the near-infrared Gaia. And this way you get the proper motions to such level of accuracy that you really start to talk about, like in the local group, you can start talk about the velocity dispersion, you can start talking about what kind of dark matter distribution is in these objects. So it would open totally new areas of research. So yes, to do Gaia in near-infrared, you need a lot of money. But if you offer me 10 billion, I'm ready to try. Okay, and what is the estimated budget of this next Gaia, next successful? There is not really an estimated budget yet, but there is the way what I explained in Gaia, that how we are operating the optical CCDs. So we are moving the image with the same speed as we are spinning. There is currently no technology in near-infrared where you could do the same thing. And I think in order to get that kind of technology in near-infrared, one needs a huge investment of money, and it's totally unclear how big that investment would need to be, and whether even that is possible to achieve such behavior. So no one knows, maybe 10 billion will be not enough. Maybe not, but then probably if you stop already earlier, if it's not possible to do it with near-infrared detectors, then you have to have a different scheme how you operate it. So it's sort of at the thinking phase, this idea. Yes, yes, nice. The another question which coming from some, okay, programmer probably. Why Java was used? Which alternatives were considered, if any? Well, this decision was made already early 2000, and I mean, maybe today one would make a different decision for the language, but at some point you are always trying to make the best guess what is the language which is most likely to be maintained in a timescale of decades, and it's always guesswork. So at that moment the guess was to go for Java.
And what it will be today, if you could estimate?
Well, I'm not myself. I'm not really an expert in programming, but I'm sure that the person who asked the question might have much better suggestion.
Okay, so another question, next question. In decades-long story of Gaia mission, what was the toughest moment? Was there a moment when did you think that mission will never fly?
There were definitely some fundamental big problems at the development phase that we had a very big issue of understanding how much harm radiation damage will cause to the CCDs. What happens is that the radiation, what we always have in space, it spoils the CCDs, and then you don't get any more nice point spread functions, and the calibration task becomes incredibly large. So in a most negative thing, one could even say that, well, the whole mission cannot work. So we put a lot of effort, and we were convinced ourselves that we can calibrate it away. And now we are in space. It's really nice. The whole thing has disappeared in the sense that the effect is much smaller than what we anticipated. Nevertheless, we start to see the radiation damage on the CCDs. So all these things, what we learned before launch, how to calibrate it, we are now taking those up again in order to calibrate the data and get the results out. But that was a sort of a scary moment that is it under control, the understanding, can we live with it or not?
And does it cost some additional money? I mean, do you start with some budget, and looking to James Webb Space Telescope, they start with 1 billion and now they are over 10 billion. So did something happen like this also to Gaia?
Yes, there were a couple of increases at the industrial phase. I think in the end we had something like 10%, 15% excess. We had to sort of things which took more time. For example, at the engineering level, we spent much more time in aligning the telescopes than what was anticipated. And when you have industry working half a year extra to align telescopes, it costs more money. So, but we didn't do any of this factor of 10 more. No, that did not happen with Gaia.
15% is dream of some missions.
Yeah, exactly. I think we are not worried of that one. I mean, this is a whole other discussion of costs of missions and how do you price them and so. But maybe time is too short to conduct that discussion now.
Okay, that one is my one question. Okay, so from all Gaia results, I like most Anna Bonacca Hole in Galaxy paper about the gap in GD1. What is your feeling about this dark impactor Konduron?
I have also heard about the presentation of this one. It's very impressive. I'm really impressed that in a way that you can go to that direction. However, it is good noting that there was a recent paper where it was sort of claimed that some of these features, what you see in these streams, can actually be just normal features coming from the galactic potential, so that you don't need any dark matter at all. So I think this is a typical hot topic which will continue and the debate. And I mean, this is the way how science works. You must have opinions which differ from the mainstream in order to make a next step in the correct direction. So I'm just happy of different interpretations because that stimulates more work.
Yes, yes, very nice detective problem. Yes. Okay, another question. Looking to the whole package of user technology, what was, from a technical point of view, most hard thing to develop? Maybe you already say so.
So is this about the hardware?
Yes, this is a user technology. Yes, this is about the hardware. Yes. What was the most hard thing to develop it? Yes.
I think in a way what is very difficult is that we require extreme stability of Gaia. We have the requirement of the stability is something which is much more than what we ever can measure on ground. So the hard technological challenge was to see to what level we can test the stability, and it's factors of tens of hundreds less than what is required in space, and then to understand the design and manufacturing that we can extrapolate based on this ground-based test with confidence that the spacecraft is going to be that stable in space, while we actually are never able to see that stability on Earth because of Earth being too disturbing.
Yes, there is question which is about same thing. It's the guy saying, or girl, I don't know. Gaia measure parallax with incredible precision. How do you manage influences as change of the orientation and vibrations of satellite?
So the astrometric solution is a global solution, which means that we are solving at the same time all the stars, but also where Gaia is pointing, and also all the calibration parameters. So you can think about it like a big matrix with several billion lines and several thousand columns. And then it's the tricky bit of this one is to control the mathematics, and in order to also with a limited CPU time. So, and in principle in this system, if you have somewhere a calibration, of course we have effects which are at the milliarcsecond level. So in order to get microarcsecond results, you have to have understanding of everything at microarcsecond level, although your sort of quantities at the single measurement level are more at the milliarcsecond level.
Yes, so very well to know what are you doing. Okay, so there is no any correction maneuvers or gyroscopes or something like that. You just know very well what you see.
Yeah, so we have this, we have active control of the spin. So what we are doing all the time, we are all the time measuring stars on the fly. And if we, because we know exactly the distances between CCDs, we know that if this star was now passing this CCD, we know exactly what time it should pass the next CCD. Okay. And if we see, and we do many stars, hundreds of stars all the time, constantly. And if we see a deviation there, we immediately know that we are spinning with the wrong speed. And we have micro thrusters which we can control at the micro-Newton level. And we can immediately, on the fly, I mean, it's an automatic loop, we can correct the spin so that we are in a way all the time adjusting this to be perfectly matching the requirement of the spin speed accuracy.
And how often this happened? I mean, these micro thrusters, I mean, pushing the satellite somehow.
In a way, there are two things what we do with the micro thrusters. So because we have this 45-degree angle, so we have to all the time compensate for the torque which we get from the solar wind. So that's by far the biggest consumption of the cold gas what we have for the micro thrusters. But for example, we have every day several tens of micrometeorite hits. And these micrometeorite hits, even though they are really small particles, but we detect them and they change the spin speed. So we have to react several times per day or a spin. We have to react to these disturbances and we correct them on the fly. So then there are always these some seconds of time lapses when we are not perfectly pointed, and then those pieces of data we have to throw away.
And you are not sensitive to solar wind pressure, I think.
We are sensitive, but that one we can correct. And of course, if there are any inhomogeneities, it's the same way how we detect micrometeorites. We detect those on the fly and correct immediately. So
your machine is sensitive to nanopascals?
I don't know from heart which unit it is, but in a way, how we approach it, that we have a certain requirement how precisely we have to follow the spin. And then it's a closed loop system where we are looking, so we are really looking the stellar, how quickly the stars are passing the focal plane, and correct immediately if we see that it's deviating automatically. It's no human intervention here.
That's nice. This seems to me like masterpiece of technology. Here is another question from Michal. Do you know about any interesting citizen science project or analysis that use Gaia data?
Yeah, we have been thinking of this one, that what would be nice things, but we haven't really come to something, because in a citizen science project, you have to have something where human brain is better than computing. And typically human brain is very good with images, but essentially we don't have images. So it's not straightforward to find a citizen science project in Gaia, but we keep our eyes open. So if there is something coming, we definitely will make one.
Yeah, thank you. Another question. How looks your typical working day? What consumes most of your time?
Most of the time, it's very variable actually. I think everyone is, it's emails about the project, things where people have issues, and then somebody has to have an opinion and guidance from the sort of management point of view. Quite a lot of meetings. So when you have 450 people doing data processing, and that's of course divided into several subgroups. So if all the subgroups have a meeting, you end up very quickly meeting every day. Of course, in my position, I have to be a little bit careful that I don't sit only in meetings, but meetings and reacting on emails is really most of my time.
How long is your typical working day?
Yeah, I usually work sort of normal 8-hour day, and then at home I do a little bit in the evening, late in the evening. So I don't know, maybe 10 hours. I mean, it's not something totally outrageous.
Yeah, okay. Another question. Do you have time for another question?
Yeah, sure.
Okay. How is the spacecraft powered? Does it use solar energy or the other sources?
It's all in solar energy, and we have lots of margin, so it's all fine. It consumes very little energy. It's a little bit the instruments, and the reason is also here because we need to have a very stable spacecraft. That's why also our antenna, which is transmitting the data down to Earth, it's not very strong, because if it would be very strong, there would be a thermal impact which would disturb the astrometry. So everything is tested exactly enough that we can detect the signal with our 35-meter dishes on Earth, but not a single watt stronger than that one, because otherwise any extra energy we use on board would disturb it. So we are very careful with the energy, and that's why it was not really an issue. Maybe a sort of sidetrack, if you're interested, is that of course when we use energy, so whatever component is using energy on board, then it heats, and so you want to have this heat production stable. Now, one thing what happens is that when we are scanning the sky, when you are in the galactic plane, you have lots of stars. So lots of stars means lots of calculations, because we have to extract these windows and make all kind of decisions on board whether we observe that or not. While if you are sort of out of the plane, then there are much less stars. So that would mean that there would be a thermal difference in galactic plane and outside of it. So what we are doing is that when we are not observing the maximum number of stars like in galactic plane, then we are faking the computers to calculate anyway that there would be stars, so that the heat production of the computer remains constant, independent of the amount of stars we are seeing at that moment.
How much computing power you use? In the nodes or the cores, if you know, because it seems to me like pretty extensive calculations. What are you doing?
Yeah, I don't know in any flop unit or anything like that, but of course computers are nowadays quite powerful. The big issue is always that to have a space qualified computer. So then it gets tricky. So we have these Maxwell boards which we are using as the for every CCD row we have a dedicated computer, and so far all of them have been working perfectly, and so we haven't had any specific hiccups there. But the precise number of flops or so I cannot remember from the top of my head.
And you mentioned that you consuming not so much of the. What is the power budget of the Gaia satellite? How much watts you need for the normal operation?
I hope I remember it correctly.
Just in order of magnitude, I like 100 or 1,000.
Yeah, a few hundred, I think, and I think.
Okay.
Yeah.
Okay, so another question. Were there any issue with the space debris in Earth orbit? How missions such as Gaia deal with probability of stray debris in the machine? I don't know, it's L2, so do you have there some debris?
Yeah, I don't think in L2. So I think maybe the only thing where it should have been taken into account is when you are doing the launch,
Yes.
because of near Earth. I think this is just a standard thing what is done in any launch campaign. There are very precise calculations of which direction you launch and when, so that you don't get hit with any of the bigger particles. Of course, the small ones we don't know. In L2, the bigger problems are micrometeorites.
Yeah, so you're so far from Earth that you don't have any space debris, basically. Okay, another question. Yep, please.
Yeah, go ahead. Yeah.
What will happen to Gaia spacecraft after the mission ends? Will it be still used for another purpose?
Well, the problem is that the electronics behind the CCDs are really not like a general electronics what you would put behind a CCD on a ground-based telescope. So in a way, it can observe only in the Gaia way. It's all sort of hard-coded in order to save energy and mass, and not to have any moving parts or anything like that. So if we cannot spin the Gaia anymore with the constant speed, then all images are blurred. So it's very difficult to find any reasonable use for something where you would have blurred images. So the cold gas, what I mentioned, what is to keep the spin stable, that is actually the limiting factor of the lifetime. So we have estimated that will run out in December 24. And after that, I don't think Gaia can be used. I mean, you could do some experiments, but really for scientific work, I don't see any use of it.
Thank you. Next question. Do you know why is there a strong increase in 2019 in the number of IPs and also papers?
The number of papers is increasing. So we made the data release in April 2018. So that's why the 18 is already a high number. It started 18, and then it was in full speed in 2019, and even 2020 we see the same speed of papers appearing. So it's all related to the Gaia data release 2.
So after the DR3, you are expecting also some increase?
I definitely, because if I read these papers, and there are so many papers which say that, okay, we have now found this one, and when we have the data release 3, we already know what to do next. So I think many groups who have been working with the Gaia data have already in their mind what they want to do when more accurate data is available.
Yes. Okay. So next question is, when you talk about metallicity, what do you mean? Are the stars made out of iron?
No, the metallicity is just a tiny little bit in the atmosphere, and what it causes, it makes the spectrum look slightly different because of the different metallicity. And the importance of the tiny little differences of metallicity is that it tells us the origin of the stars. So it tells about when in time they were formed, and also, for example, stars which have been forming in one of the local group dwarf galaxies, which have been then coming into our Milky Way, they typically share the same metallicity, and that is different from the metallicity in general in our Milky Way stars. So it's like an extra element in addition to the motion, which can give us hints about the origin of the stars.
Thank you. Because you mentioned in your presentation that Gaia's biggest catalog, here we have a question. Gaia's biggest catalog dataset in astrophysics or whole science?
I think astrophysics, because I would think that if you go really to huge data flows, if I don't know exact numbers, but for example, CERN, when they make these particle experiments, and they talk about incredible number of measurements, and so I'm sure you can. I think in a way what we say in Gaia is that the catalog is enormous. It's really huge, exceptionally large, even in all fields of astronomy. The CPU power, what we need, especially for the astrometric solution, is also huge. So neither the CPU power is the largest, whatever you can think, nor the size is largest ever, but it's the combination. It is pretty large and it is pretty complicated, and then to try to manage the amount with the complexity, that makes Gaia rather unique. It's the combination which makes it difficult.
Last two questions. So you probably did many public presentations for Gaia. Is there a question from audience which you remember as special, for example, because it was funny?
No, I think like here, you have very valid questions. So there is not really a sort of peculiar question anywhere, not that I remember, no.
Okay, last question is why there are more dim stars in DR1 than in DR2, with mean G bigger than 22. So probably guys assuming that with next delays you have more stars in every category.
Yeah, so what this is probably reflecting to the histograms I showed, where there were very faint stars in the data release 1, which are not existing anymore in data release 2. But most of these are actually most likely false detections, and now with the data release 2, we have much better. So we have to see the same star several times before we approve it to the catalog. So many of these faint stars, which might be, I mean, there might be true objects which have been bright in a certain moment and then disappeared. We don't know. But we have been weeding out quite a lot of false detections. And so in a way, the sample is cleaner. And this means that some of the faint false detections have fallen out.
So, okay, thank you very much for your answers and for your presentation. We very appreciate it. And I think that I could wish you that you should have next mission, because it seems to me that you have the army of very well prepared people to solve the very hard technical and science problems. So it will be good to have another guy after this one. So thank you very much.
Thanks to you, and it was a pleasure to talk to you. And of course, I was presenting like myself, but as I tried to emphasize, I'm presenting on behalf of many people who have been contributing to Gaia.
It's over 1,000 people there, I think, in the collaboration of the Gaia.
Yeah, yeah, exactly.
Okay, thank you.